Hello and welcome to class 2 of particle fundamentals and fuzzy logic. So in this class, we're going to apply some concepts we learned in the previous class, such as velocity and timer, and we're going to make the particle pulse and follow the target. Okay, so here's what we've done in the previous class. We've got a target vector, a system that adds based on this target vector to the velocity. We've got a timer and just a little bit of drag. So let's combine these two things in the same node. And we'll just keep this off to the side for now. The first thing I want to take a more thorough look at is the velocity. Okay, so let's just get rid of that. We can call this seeking behavior. Okay, so the target vector is going to be fairly universal. Target vector. And let's view that. Whereas our direction and our seeking behavior will be much more specialized. Okay, so diving in, let's first start by just having a generic mechanism to add anything to the velocity. So starting off quite simply, we still need the target vector, but I'm just going to clean up this velocity just a little bit. So we need more or less a generic mechanism. Let's just Control C and Control V out of here. And I just want more or less a standalone way to make this feedback loop. Okay, so we're just going to add our normalized direction. And here I'm just going to make a null, and we'll call this shark direction. So everything custom that we do in the system, it's good to have a naming convention. So everything in this case will start with shark. And a direction is very different than a vector, because a vector can have a length. The direction is really just going to be a unit length. So that's where the normalize is coming in. So shark direction. Okay. And we want to be able to control how quickly it moves based on the distance. So this is a little bit too simplistic. So we can call this something like seek, maybe shark seek speed low. All right, so we got that. And then we'll also have a shark seek speed high. And at the interface level, you can see we have these two, shark seek speed low, shark seek speed high. We'll be able to override those later with particle attributes and also in softs. All right, so just editing that interface a little bit to keep them together. All right, so let's just start off with a 2-second seek speed, the same seek speed for both of them. All right, and what we want to do is we want to base the seek speed based on distance. So how do we get the distance? So here's our velocity. We need to add something to this velocity in here. So what we can do is we already have the distance present in this target vector. Wherever the target is going, let's just turn this off. So wherever the target moves to, it's going to have a new length, and this is really the distance to our vector. So what we can do is we can have a length fob to give us the length of this vector. Okay, so in comes the target vector, and this would be the target distance. Now, we don't really know or even care in this kind of methodology how far away this is in actual units. What we really care about is what is far and what is near. All right, so near I definitely think would be 0. So we really need a relative distance. So for that, we can use a fit. All right, so we're going from 0, and then we don't know what this number is. So I'm going to promote this, and we can say shark seek distance high. Okay. And then what that's going to do is it's going to fit it to a range we can work with, meaning near and far. And now, because we have this in the 0 to 1 value, let's say we want our seek distance that's representative of far away to be, I don't know, 5 meters. Then now we've given it relative values, and we can follow that up with a ramp. We'll call this seek distance ramp. We want a floating point ramp. Now don't try to adjust it in here because this is the default. So we want to adjust our curve at the interface level. So right now if we use this as a multiplier, it wouldn't seek at all if it was near, and it would seek a lot if it was far away. So yeah, that's about right. And like most things in nature, it's going to follow an exponential curve. So here I want it to kind of be a little less interested if it's close by, and I want it to be increasingly interested as it's far away. So that'd be a fairly standard curve for I think what we're trying to achieve. All right, and I really want to test out these distances. So let's get a color preview going on here and really get a good distance for our seek distance. I'm going to make an attribute called distance test vector export. And let's just make this the distance that we're after. So here's the normalized distance, and here's our maximum distance. So we're going to multiply So multiply this unit length vector by the distance high. And it's important this goes on the bottom so we can multiply the x, y, z of the vector. Okay. All right, so now let's make a preview for that. Okay, so that's bright red so that it's easy to see. And as we switch our target, okay, so it's always going to maintain the same length. Okay, so this is our distance that we would deem as far away, and 0 is of course close by. All right. So based on this distance, we want to add a low or a high value to the velocity. Okay, so here's our 0 to 1 values. And we'll just redo these chains of events here. Here's our shark direction. So I'm going to fit the result of the ramp from 0 to 1, and it's going to be fit to the low speed and the high speed. So we can deem whatever we think it should swim if it's this far away, or whatever we think it should swim when it's this far away. And now finally, let's add this to the velocity. We can take the shark direction, multiply it by the increment which is here. The increment that's going to add to it each time. All right, so here's the shark direction coming in. Here's what we want to add to it each time. All right, now here we can just plug this in. Now, in order to keep this thing, this velocity under check no matter what the time is, whatever the frame rate and the subsamples and all that are, we're just gonna, right before we add something in, we wanna account for the time increment. Okay, so I'm just gonna go in here and get the time increment and multiply the vector by also by the time increment. Okay, and let's just encapsulate these. We can call this add to v. All right, so we have a little mechanism that we can keep adding stuff to. Let's try it out. So it should all be moving at the same speed right now because it's 2 and 2. Let's also get a color preview going based on how far away it is. So let's see. So here's our ramp. So in comes the bias. If it's far away, or if it's uninterested, I should say if it's close by, we want to make that 1. If it's far away and wants to accelerate more, we can make it red. Make sure you disconnect any other color previews that might be happening. Okay, so we should get a color preview. Red if it's far away. As it comes near, it's going to get close. And now it's red again. Okay. So let's add some interest. Now on the seeking behavior, top level, let's say that if it's close by and fairly uninterested, let's go by 0.5. And if it's far away, we want it to move a little more aggressively. And let's also get the shark on here so we can kind of gauge the distance in a relative way to the scale. One little change I'm making just so that the shark is oriented correctly is I'm turning this from a null into a parameter shark deer. Okay, so that it will detect the direction and rotate our model. Okay, so we can gauge from this kind of how fast this thing's supposed to move. And I want it to move just a little bit faster. Okay, so the values I arrived on was a high speed of 4.5 and a low speed of 0.25. And now we can see the shark. Once he knows where he's going, he swims pretty fast and then slows down. All right, as the target changes, pretty fast and slowing down. Okay. So now let's integrate the timer. So our previous timer setup, let's just convert this to something we can use to, instead of do a constant addition to the velocity, we're going to do pulses, very similar to a swim cycle. And the farther it is away, the more it's going to try to swim to catch up. And if it's very close by, maybe we don't want it to swim as fast. So back to our relative distance. This would be our relative distance. And do another fit. And this time we want to fit this to what we want the pulse rate to be when it's needing to swim fast. So we can call this pulse rate high. And a pulse rate low. Okay, so what's our previous pulse rate? Previous timer increment. Okay, well, that wasn't set. So let's just say we want, if it's far away, we want maybe 3 pulses per second. And if it's pretty close by, we want to pulse every half second. All right, so there's our pulse rate. It's all per second. All right, now we have to convert that to an increment. So now we would just want to do 1 over the value. Okay, and often if I'm trying to preview things, a good place to do that is in the color. Just to get a really quick color value. It's very important not to try to do all of these steps in one go. Most assuredly make some type of mistake. Okay, so far away, we've got a pulse rate of 3. As it gets closer, see the pulse rate is much faster. Okay, so let's apply this now. So here's our old timer increment. I'm just going to get rid of that. And let's plug in to say if it's greater than this timer increment. And remember, it's adding a time increment on every frame. Is the timer greater than it should be? So it's allowed to get a little farther when it's nearby. And then as it's pretty far away, see it's just not allowed to get that high. Just for a preview, let's just show what it's supposed to be, what its maximum value should be. Okay. So here it's only allowed to get to this value. Keeps going, keeps going. So it hasn't reached the threshold yet. And then finally, it reset because it's larger than the timer increment. Okay, and now let's see what that looks like in the color. So this timer increment would need to be replaced as well with this value. And let's see what that looks like in a red and white preview. Okay, so it's definitely not going to try to swim as much if it's close by. And then it really takes off. Okay, so now let's form a connection between the timer and this the velocity that it's being added. Let's rename this curve to pulse curve. And we have to think about how we want this pulse to increase and decrease. So with this pulse curve, I think it should, as a tail swishes on one side, it wouldn't affect the velocity much at first, but it would affect the velocity pretty quickly thereafter. It's going to have most of its acceleration in the front part of the envelope, and then it's going to trail off in its effect as it pushes more and more to the side. So we can have a sharp attack and a gradual fall off with the velocity that's being added. There we go. Okay, so let's try this out. So here's the result of our it's a scalar value, result of our timer being remapped. And now let's apply that as a multiplier to the speed. So it's already gonna go the right speed because we set that speed up. Okay. And now we'll just multiply this float before it gets added to the shark direction. Here's our pulse curve, 0 to 1, multiplying that. Okay. And I think it's a pretty important diagnostic to see what we're actually doing to the velocity here. So I'm going to make a parameter, let's call this test A. And let's preview these pulses as they're getting added. There we go. Let's make that orange. All right. So now we're not adding a constant anymore. We're adding pulses of velocity that correspond with the envelope. And you can imagine the tail going back and forth and swimming. Every time we see the dot get red and white, that means it's going to swim a little bit. Now let's increase the speed that's added to compensate for the fact that it's not being added constantly. So here I'll just multiply these by 3. Just to give a better look here. Okay, so he's really taken off, but not adapting as much if he's close by. There we go. Okay, so now we've successfully combined a timer with the ability to adapt its speed, and that's all based on distance. We've got speed that's being added based on low and high distance, and we've got a pulse rate based on low and high distance, 6 pulses per second if it's far away, a pulse every 2 seconds if it's close by. Taking a look at the full setup, we've successfully done the distance. We've done a timer with feedback, a lookup curve, and we're adding that to the velocity. Now let's take this in a slightly more advanced direction, and similar to how an animal might actually behave. So if it wouldn't just keep accelerating into infinity, what we'd probably want to do is we'd have a target speed, a maximum speed that it would reach. And once it reaches that, it's really going to stop swimming, stop pulsing until it feels the need to do that again. So to do that, we have to have a level of abstraction. And that's really how I like to engineer really complex systems. So get it to work on a simplistic level first, and then once it is working, take a step back and abstract that. So let's give this a target speed that it has to reach instead of instead of simply adding with brute force these values. We were pretty happy with our target velocities. Let's say this is our target speed if it's nearby, and this is our target speed if it's far away. And really, we just want to keep adding to the velocities until it reaches whatever speed we deem necessary. All right. So this is the speed low and the speed high. And let's measure the incoming velocity to see how different is this. So in comes the velocity. And now let's get the length of the velocity to determine how quickly is this traveling. And let's just export that. We'll call this shark speed so we can test it out. Maybe a diag for diagnostic shark speed. Okay. So we really want the speed to approach these speeds. So let's see how different this is from our desired speed. So here I'm going to subtract the current speed from the desired speed. Okay, and we don't really want to slow down. So for that, if this is higher than this, we would just maybe do a clamp. And let's clamp. Let's set this to a pretty high number. Okay, so now it's just not going to go below 0. Okay. And just because this is getting to be a lot of wires, let's just call this whole thing, by collapsing, speed difference. And I'm just going to put the output of that into the sub output. So this is our speed difference based on what we want to be versus what we're at. All right, and now we want to turn this into a relative value so that we can make decisions based on that. So for that, we want to know, okay, here's the current speed difference. What's the maximum speed difference that could actually happen? So the maximum speed difference would really be the high speed minus the low speed. So I'm just going to subtract these two guys. So this is the maximum it could be, and this is the current value. So you might know where this is going at this point. So here, we're going to fit the current speed difference from no speed difference to the maximum speed difference to the 0 to 1 range. And now we're powerful. Now we can have a lookup curve to determine how much we should pulse. Let's call this pulse intensity ramp. All right. And if it's very different from the desired speed, then we want it to pulse a lot. If it's not different, then we don't want it to pulse at all. And let's just do, once again, more of a ease in, ease out curve to make that decision, to adjust those values. Okay, so instead of an absolute pulse rate being plugged in here, I'm just going to put in our relative values. Pulse intensity ramp would determine if we have pulse rate low or pulse rate high. Okay, and now these are our desired speeds. Okay, so the only problem here is that the desired speeds are adding in to the same thing as is being calculated. So we might want to have different values to control the speed versus how much is added on every pulse. So for that, let's just make another fit. Okay, so this fit is responsible for getting if it's close or far away from the desired speed. But we want a different fit in order to actually add to the velocity. Okay. So this can be pulse intensity low. And pulse intensity high. All right, and let's find a fairly low adaptation to get to the desired speed. So let's just try out 1 for now. Let's see if this works. See, so it's not adding much at all, even though it's trying to. It's trying to get to that high speed. It's just not getting there. Okay, so let's give it a little help. Okay, so that's a good low adaptation speed is 1. Let's see how 10 works. So after playing with the values a little bit, I've got a pulse intensity, meaning 8 is going to be added to the velocity, and 1 is going to be added to the velocity, depending on how much it needs to maintain its speed. We should probably just go to don't add to the velocity at all. There we go. All right. So from this class, we used our velocity to seek a target. We used a timer and a series of curves in order to adapt its behavior in time-based increments, and we're adjusting the timer and the velocity based on a factor, which is distance. And then finally, we took a certain level of abstraction, and we're saying if it's already swimming at its maximum speed, then don't try to swim anymore. So we're adjusting the pulse intensity based on the desired speed versus the current speed. In the next class, we're going to take a look at some rotations and how to also adapt to the directionality of the seeking behavior.